Okay, yeah, thanks, Martin. I think last year when I spoke at this convention, I began my talk by saying something like, and now for something completely different. It's really actually great that it's not quite so different as it was last year. As Martin was saying, there's been a lot of discussion that's been happening. There's also been a lot of great work that's been going on with some folks from the GNURadio community in collaboration with the SETI Institute and with Breakthrough Listen. So for those of you who weren't here last year, I would like to give you a little bit of background on how we actually do the kind of searches that we're doing, some of the equipment that we're using, and some of the algorithms. Thanks. But I'd also like to highlight opportunities for people in this audience to get involved. There's a great range of skills here. We've already had, as I say, kind of quite a lot of involvement. I really want to kind of give a big shout out to Ben Hilburn in particular and to Mike Piscopo, Mike in particular, who came back out to the Allen Telescope Array to work with some of the undergrads out there this summer. But also to all the other people who came to the hackathon, who've been working on modules for GNURadio that are going to help really hopefully give you access to some exciting hardware, to some exciting data that we've been taking, and also maybe help us make what we think is one of the most profound discoveries in science. So, as Martin mentioned, I'm based at UC Berkeley, at the UC Berkeley SETI Research Center. I'm also affiliated with the SETI Institute, as is my boss, Dr. Andrew Siemion, who is the principal investigator on the Breakthrough Listen project, which I'll get to later in the talk. But Breakthrough Listen has really revolutionized the search for intelligent life beyond Earth in the last few years. Oops, okay. So, obviously, you're all familiar with the RTL SDR hardware. We've really had fun playing around with this with some of our undergrads and kind of getting them a little bit more hands-on. I mean, I did my undergrad and my PhD really pretty much as an end user of the instruments. You know, you sort of point at something and then data comes out the back end and it's a little bit of a black box. So it's been kind of really cool to get our undergrads a little bit more engaged with looking at some of the hardware. And really what we're doing with the kind of experiments that we're doing, which again I'm going to get to in a little bit, is scaling this up. Just more bandwidth, more sensitivity, really trying to maximize the amount of data that we can take in pursuit of this search. Little antennas, I'll show you some bigger antennas than this a little bit later on in the talk. But the data really looks pretty similar to what you get if you fire up something like GQRX, these waterfall plots. So I think most of you are familiar with this, where you have frequency on the horizontal axis and then time scrolling down on the vertical axis and the intensity represented as the colors here. And there's a lot of signals out there. It turns out that there's a lot of hardware, particularly in a room like this. I think there's probably sort of a higher density of RF signals in this room than there would be in pretty much any other place with this number of people in it, given the audience here. But there's a lot of transmitters that are transmitting information between themselves and to base stations, and you know, modern life really is full of these transmitters. And really the idea that motivates the SETI search is the search for extraterrestrial intelligence is, well, if there's life elsewhere, maybe they've developed technology too. And so actually we've come up with this term, Jill Tarter, who's one of the pioneers in the field, I think has really been promoting this idea of techno signatures, which again I'm going to get to in a little bit. But it's the idea that you could look for signatures of technology. And people sometimes come along and they say, well, you know, what if their technology is, you know, tachyons, or what if their technology is subspace communicators or whatever. And my response to that really is, well, if you can design a subspace detector, then we'll put it on the telescope. But until then, we're really kind of motivated by the idea that an advanced civilization may still choose, for very good reasons, I think, that probably I don't need to explain to many people in this room, may still choose to use radio for some of their communications, or maybe actually to make their presence known to other folks like us that are out there looking for them. So again, a lot of technology that's out here. A lot of devices that are communicating with each other, a lot of frequencies that are in use across the spectrum. It used to be that astronomy used just a few little very narrow reserved bands, but now we have these wide bandwidth detectors, and we have to contend with the fact that there are all of these devices that are using regions of the spectrum. And you know, we don't know if they are out there. We don't know which frequencies they might be transmitting on. Again, we don't know whether they might be using radio, but we actually really just feel like we have to go out and do the experiment, right? We can sit here and talk about this, or we can actually go out and gather some data. So I want to take you back sort of half a millennium when there were 7 planets, interestingly, including the sun and the moon. These were the classical planets that moved across the sky. But of course, 500 years ago, the beginning of the modern scientific revolution in astronomy, the realization that there was empirical evidence that the sun was the center of our solar system, that the moon was a satellite that was orbiting the Earth, and that the other planets were planets that were just like our own. Obviously, the figures like Galileo and Copernicus that were really very instrumental in this, and I guess the term instrumental actually also applies to the fact that they were among the first scientists to really use modern scientific instruments to actually understand our place in the universe, to use the telescope. Telescopes, of course, have been developed in the 500 years since. But this is really, a paradigm shift. Our realizing that we're not at the center of things, our realizing that we're not maybe all that special, or maybe we are, but at least the history of scientific observation in astronomy has shown us that when we think we're kind of an outlier, that when we think we're unusual, we actually realize we're not. We're on an average planet going around an average star in an average galaxy, and maybe the average world in our galaxy is also inhabited. And in fact, Giordano Bruno, you see a statue of him here in Rome, was burnt at the stake in 1600 for daring to suggest, as the Roman Inquisition said in their summary of the trial, that there were many worlds, many suns necessarily containing similar things in kind and in species as in this world, and even men. So this was really a heresy back then, a little over 400 years ago, but it's still a question that we don't have the answer to. Are these worlds out there inhabited? One of the things that we do know now that has changed, I don't know where I'm supposed to point this, but there we go. In the intervening period, and particularly in the last 30 years, right, is that we've discovered planets outside our own solar system. There were no planets. When I was in elementary school, there were 9 planets. I apologize to those of you who are offended that Pluto got demoted. I didn't have anything to do with that. But in exchange for sort of switching to 8 in our solar system, the astronomical community has discovered thousands of planets outside our solar system, and really the implication is that there are perhaps hundreds of billions of planets just in our own galaxy. And we're not at the stage yet where we know if any of those are inhabited, but that's the next thing that we want to try and find out. There are some of those systems where there are multiple small rocky worlds that are in the sort of temperate zone, in the habitable zone around their star, where the temperatures might be right for liquid water to exist on the surface. Here's one example, artist's impression of the TRAPPIST-1 system. But again, there's hundreds of billions of stars in our galaxy, and the results from missions like the Kepler spacecraft have shown us in the last few years that pretty much every star in the sky has at least one planet going around it, and maybe something like 20 or 30% of those stars have these small habitable planets going around them. There are missions that are in the pipeline that are going to look for biosignatures, things like the James Webb Space Telescope and some of the big 30-meter class telescopes that are being built on the ground. That might be able to look for signs of biological processes in atmospheres, maybe looking, as you see in these infrared spectra here on the left, comparing Earth with Venus and Mars, that you can see water vapor, you can see ozone, you can see other signs of biology, of non-equilibrium chemistry in the atmospheres of planets. And again, sort of by extension from this, the idea that we might be able to remote sense signs of biology, maybe we could also remote sense signs of technology. This slide is just to illustrate really that the remote sensing biology is hard because the light of a planet compared to the light of a star is very faint. You have a real contrast issue. It's like looking for a firefly next to a searchlight. But in certain wavebands, in certain radio wavebands in particular, in a narrow band, the Earth actually outshines the sun at radio wavelengths, so we don't have this contrast issue. There's still a sensitivity issue. You still need big dishes. But these techno signatures, some of them are at least in principle, detectable over interstellar distances. So some of our brightest transmitters, and particularly some of our most directional transmitters, things like the Arecibo radar, big dish in Puerto Rico, if you pointed that at a similar analog dish under sort of favorable circumstances, you could pick that up to a few hundred light years away from Earth. One of the seminal papers in the field, actually its 60th anniversary is coming up tomorrow, this paper in Nature by Ciccone and Morrison, which really did some of these sort of back-of-the-envelope calculations of the feasibility of doing a radio SETI search. And then the following year, young astronomer Frank Drake, many of you will probably be familiar with the Drake equation, used a telescope at Green Bank with one single steerable channel. Frank looked at 2 stars, and he searched through those with just a loudspeaker hooked up to the output. He heard some kind of weird sounds coming out, which he later figured out, I think at least one of them was an airplane going past. The first example of the thing that we struggle with still, it's the radio frequency interference from all of the devices that we have ourselves as a human species. This motivates the search, but it also really hampers the search because you have to listen through this din of devices to try and pick up something that would be coming from interstellar distances, and hence, even if the transmitter is very luminous, then the signal that you're going to pick up is going to be very, very faint. Mike Garrett, the director of the Jodrell Bank Observatory in the UK, has sort of parameterized this multi-dimensional haystack that we have to search through to succeed in this. So you have things like spatial resolution, field of view, sensitivity or depth, bandwidth, polarization, temporal resolution, frequency resolution, and then there's the actual signal type. There's data processing, maybe AI and machine learning in pursuit of signal recognition. So even if you can maximize, if you have a big dish and you can go very sensitive, and even, well, the problem with a big dish is that you're compromising on field of view. There's a lot of kind of sliders that you have to move around, basically, that are going to have to be optimized in order to do the kind of search that you're interested in. But even having all of that data, you still have to be able to recognize the signal when it's in there. So we're sort of digging around in this haystack. We're not even sure that there's a needle in there or what the needle might look like, but we have some ideas. So in 2015, the Breakthrough Prize Foundation announced the launch of the Breakthrough Listen project, $100 million over 10 years to really accelerate the search for extraterrestrial intelligence. There was a lot of media interest. My boss, Andrew, sent me off to do the Fox Business interview where I think they were interested in the 100 million figure and sort of didn't really have a clue about the science. So there were some nice graphics of like the lunar rover and astronauts in orbit and sort of things that really were not very germane to the subject. And the interviewer was asking me, what might the aliens look like? And I was sort of tempted to say, well, you know, they might look a little bit like you, waving your arms around like now, I don't know. But you know, we really want to actually bring the scientific approach to the search. We don't just want to speculate. We don't want to put our tinfoil hats on. We want to take a lot of data, and we want to see what we can do with it. We are taking a lot of data. The telescopes in the top row are the primary observing facilities right now for Breakthrough Listen. The 100-meter Greenbank Telescope in West Virginia, it's the largest movable dish in the world, and it's actually, after the sarcophagus that they slid in over the remains of the Chernobyl nuclear reactor, it's the second largest movable structure on land. The Parkes Telescope in Australia, which was used for receiving some of the transmissions from the Apollo missions. The Meerkat Telescope in South Africa, which is one of the precursor telescopes of the Square Kilometre Array. And then we have an optical search that's going on with the Automated Planet Finder at Lick Observatory in California. In the next row, you see I mentioned Jodrell Bank. That's the biggest dish in the UK. The FAST telescope in China, new dish, which is the largest in the world, although it's not steerable. It's built into this karst depression in the mountains. And then we just announced the launch of a search using Veritas, which is a pretty interesting optical telescope that's actually strangely looking for gamma ray sources as gamma rays hit the upper atmosphere, but we're going to use it to look for bright optical pulses. And then at the bottom you see some of these aperture arrays, these sort of new generation of telescopes where we're replacing the large amounts of steel in something like the Greenbank telescope with silicon on the back end, and actually doing things like phasing things up, doing beamforming, doing correlation, and replacing sort of these large dishes with electronic methods that allow us to get the collecting area and resolution and sensitivity that we want. So there's the Greenbank telescope again. That's our chief engineer, Dave McMahon. For scale, you can see some folks who rappelled down from painting the underside of the dish there, just about make them out, and some trucks in the foreground for scale. It's a really pretty impressive piece of engineering. You can actually go and visit the site. They have some tours actually that also specifically include some of the work that we're doing there. It's kind of fun. And it's in the National Radio Quiet Zone, a few hours west of Washington, D.C. There's a few papers here that talk about the infrastructure that we built. So there's fast compute clusters that are deployed at both the Parkes Telescope and at Greenbank. And then the third reference there is to the data archiving, which we're doing. We now have about a petabyte of public data that's available. And we have now, with the system at Greenbank, 12 gigahertz of instantaneous bandwidth. We have about 8 petabytes of storage on site. And we're streaming data to disk at really kind of honestly unmanageable rates. I mean, to the extent where right now we're just archiving the waterfall plots. We're archiving essentially just the total power information with some compromised resolution and time resolution. And that, you know, we have the IQ data, we have the raw data that's coming in, and we're sort of scaling up to be able to do analysis on the raw data. But right now, the focus of most of what we're doing is on these waterfall plots, is on the IQ data, and we have some of those. We have some of the raw data publicly available. We also have some of the IQ data publicly available. The files are big, but the raw data and the IQ. We have the waterfall plots available as well, including some in SIGMF format. And that's pretty easy. There's tools as well, that'll enable you to load that into Python and to actually look at some of the signals that we're picking up. I'll skip over this in the interest of time, but we have different frequency and time resolutions that we generate in terms of these waterfall plot data. And this is maybe of interest to some folks in the room here. I don't know whether many of you, has anybody heard of CASPER, the Collaboration for Astronomy Signal Processing and Engineering Research? A couple of folks in the back who are maybe radio astronomers. So CASPER is essentially using commercial off-the-shelf hardware rather than doing sort of bespoke interconnects, doing sort of designing instruments that are just specific to the experiment that you want to do. CASPER basically tries to get everything into Ethernet packets as quickly as you can. So this is the snap board, which is the latest iteration of the boards that digitizes and then actually kind of runs stuff through the FPGA and outputs the data that you're interested in. And so this is kind of another interesting open source project that some of you might want to check out. Some of you may even want to get on the CASPER mailing list and kind of potentially see what's going on there. So as I mentioned, we get waterfall plots out. This is just a waterfall plot of 5 minutes of data, 187.5 megahertz of bandwidth for one of the nodes in our compute cluster at Green Bank. And you can see there's some kind of squiggles in here, some signals. The vertical lines are just part of the filter bank, basically, that we're using here. And again, sort of we don't think we picked up ET. We think that we picked up a bunch of other things of our own devices. But there's one way that we can actually use a spatial filter to try and discriminate against some of that local interference, and that's because the beam of the Green Bank telescope, because it's 100 meters, and your resolution, your width of that beam goes as wavelength divided by the diameter of the dish. So with a 100-meter dish, you have something like a 1/10 of a degree resolution on the sky. So you point this thing pretty precisely, and then you can actually nod on and off the target that you're interested in. So here's that waterfall plot again. Here's an off pointing, so we move to a nearby pointing about a degree away. And then we do on, off, on, off, on, off in 3 pairs of observations. And so the top row here is when we're actually pointed at the star that we're interested in. The bottom row is when we're pointed at a neighboring star that's not our primary target. And essentially the search amounts to just look for things that are in the top row that are absent in the bottom row. And for those of you who are kind of carefully paying attention here, you can probably see there's something at about 2.4 gigahertz, which is probably, I'm assuming, somebody who's ignored the signs around the telescope saying, please turn off your cell phone and turn off your Wi-Fi. So we pick that up whether we're pointed at the star or not. We'd like to be able to draw boxes around these and actually figure out what they are. We've been chatting with Ben and folks at DeepSig about smart ways of doing this. I kind of really hope that ET is actually doing something like this, so that they might be sort of transmitting something that really looks anomalous, that looks like an outlier that we might be able to pick up, although actually our current algorithms would probably miss even sort of weird shapes like this. But that's pretty obviously something that's happening like that when we're pointed at the star. We'd want to go back and look at that star again. There's a lot of satellites overhead. I mentioned this in the workshop that Mike ran yesterday. There's some nice free software called Stellarium where you can actually visualize satellites that are overhead. But we also have some undergrads that have been working with us who have been doing satellite path prediction. And here you can see a GPS satellite, the distance on the left-hand plots of these GPS satellites during the 5 minutes of the observation, and then the corresponding waterfall plots on the right. And you can see there's some clear correspondence between the satellite that was going over and the interference that we're getting. We're actually getting FFT overflow in the bottom plot here, and this is kind of bleeding out into the neighboring channels there. So I mentioned there's about 1 petabyte of public data that's available, both spectrograms and some IQ data. We have results that were presented from our analysis of 1,300 nearby stars that are on this website, which you can go look up later. We're beginning to look at neighboring galaxies. That's sort of what's coming up next for the program at Green Bank. So here you're looking at things that are maybe 100,000 times further away than the star sample, and so the transmitters here would have to be basically 10 to the 10 times as bright. But then if you think of the scale of a galaxy, and if you're familiar with the Kardashev scale, some of you probably are, that actually corresponds to the difference between a civilization that's using all of the energy from its parent star, type 2 civilization, to a civilization that's using all of the energy from its entire galaxy, a type 3 civilization. And so we're actually kind of interestingly, sort of coincidentally, sensitive to these different scales over galactic distances. And so we hope to be able to put some limits, or I mean hopefully a detection, but at least some limits on the prevalence of civilizations like this too. I'm going to skip this just in the interest of time. This was some graphics that we had corresponding. This went out with a press release about using a machine learning algorithm to find fast radio bursts. So fast radio bursts are these weird, bright bursts that we still don't know what the origins of them are. Some people have suggested maybe it's ET. I don't think it is. I think aliens should never be your first thing that you run to. They should be sort of the last thing when you've ruled everything out. But they're pretty interesting in particular because they actually sort of stand in as proxies for these sort of bright bursts, maybe brief in time or narrow in frequency that we're hoping to detect with these algorithms. So we had a grad student working with us who did some work using machine learning algorithms, particularly CNNs, to try and detect these. Nobody actually figured out, I don't think, and maybe this audience, it would be good for to draw this to your attention, that there's a kind of secret code that's hidden in this image. You might want to go have a look at that at some point later. So this is what he found. Basically, the ones in red, I think, were the ones that were missed by the classical algorithm. So he's finding bursts that were coming from this source, from a source called FRB 121102, that were missed by the existing analysis, and which his CNN was able to pick out. So some interesting sort of machine learning applications here. There's also some work going on with anomaly detection. Again, the same student here. So there's some real data on the left, and this is each individual sort of pair, or I guess there's like 5 rectangles here, 5 pairs of individual rectangles on the left, 5 pairs on the right. And these are, I have a laser here. So you have an on observation and an off observation, then another on and an off, an on and an off, on and off, on and off. And Jerry here did some work that was basically doing forward predictions. This is simulated data on the right, and he's predicting what you should see in the off based on what you saw in the on. And in the 4th line here, you can see he predicts that this signal in the on observation should continue. In the off observation, it doesn't actually do so in the real data. And so these are the kind of anomalies that we're looking for, where you might be able to compare real and simulated and say, oh, that looks different. So that's maybe kind of something that we might flag as a candidate. How long do I have, Martin? Just a couple of minutes. Okay. Here's a detection of extraterrestrial intelligence. This is one of the Voyager spacecraft. So it's unfortunately our extraterrestrial intelligence, but you can go find this in some of the data files that we have online. It's really kind of fun how you can zoom in from a data set like this and then actually see the carrier and the data signals here. Go have a play with that. There's, again, you can look at this on my slide deck later, but there's kind of a brief intro that I wrote about sort of some of the background that I've kind of really whizzed through too fast here in this talk, how we actually go about doing these searches. On Monday, we had an announcement about the upgrade to the Allen Telescope array. So some of you were out at our hackathon at the ATA, and we're hoping to do this again next year, get some GNURadio folks out there, really kind of get hands-on with this. And then there is actually some software that's come out of that enables you to read data from this array into GNURadio. Some data that's available there in SIGMF format. And then, as was already announced here, next year the GNURadio conference is going to be co-sponsored by the SETI Institute, Breakthrough, and Berkeley SETI. We have undergraduate internships. If you are an undergrad or know undergrads who might like to come and work with us for a paid internship during the summer, we also are trying to ramp up our hiring, particularly with the ATA as a result of this extra funding that's come in from Franklin Antonio. So keep an eye out for that. If you want to join our Slack, there's a number of people in this room who are already on Slack who are talking through some of these things. You're welcome to do so. Also some outreach stuff. Jim Shea was kind enough to come to an event in London where we were demoing some of this stuff in the context of the SETI search. More educational stuff that's going on. I mentioned already the work that Mike is doing. And just to finish, and apologies again for sort of the whirlwind tour of this, but celebrating this anniversary tomorrow of this paper by Cocconi and Morrison, they end that paper by saying, basically, we don't know what our chances of success are, but if we don't search, the chance of success is 0. Thanks.
We do have time for 1 or 2 questions.
You had mentioned simulation? Do you simulate the whole 12 gigahertz bandwidth?
No. So Jerry there was taking little chunks, and basically, so there's two things that we've done. One is just inserting simulated signals and then seeing how well we can retrieve them, and the other is just concentrating on small regions of the spectrum with signals in. So that 12 gigahertz is mostly uninteresting. I mean, depending on the sensitivity thresholds that you set, you can extract potentially millions of signals from that sort of bandwidth. But there's a lot of channels that are just full of noise, and we want to just ignore those basically and do simple energy detection on that.
Okay, no hands up. So thank you one more time. And please.